Hi students, I hope you are all doing well. Today we'll be discussing about the soil water relationship, which is a second lecture of irrigation water management. So without any delay, let's go into the topic. So in this topic, we'll be discussing about the different aspects of soil water relationship. We'll study first the physical properties of soil, physical properties of water, soil water, soil water content, measurement of soil water or soil moisture, then energy state of water, then flow of water into the soil and in the soil. Okay, so you must be aware of different physical properties of soil like soil texture, soil structure, soil color, soil temperature, soil aeration and all. So for studying in deep the soil water relationship, we must be aware of the soil physical properties. There are two most important soil physical properties are soil texture and soil structure. Soil texture, you might be knowing, this is the proportion of sand silt clay or primary particles. Sand silt clay, this is the proportion of sand silt clay, and the structure is called as the type of arrangement of this sand silt and clay is called soil structure. Okay, so there are two classification of soil texture. Okay, one is USDA classification, United States Department of Agriculture, and the second class is International Society of Soil Science. Okay, which India adopts. India adopted this classification, ISSS classification. Okay, so according to USDA classification, there are 8 classes. Okay, starting from gravel, which is more than 2 mm, coarse sand 2 to 1 mm, then 1 to 0.5 mm, which becomes your coarse sand, then medium sand is 0.5 to 0.25, fine sand 0.25 to 0.1, very fine sand 0.1 to 0.05 mm. So the most important thing is here is the clay size of the clay particle, which is less than 0.002. Similarly, in the ISSS class, the clay size remains same, but others it differs. Okay, so we have here gravels 2 mm, same 2 mm, coarse sand 2 to 0.2, but here it is 1 to 0.5. Then silt particle ranges from 0.02 to 0.002. Okay, this is the thing. Then the thing is, where is the headquarter of International Society of Soil Science? Okay, it is at Vienna, Austria. Okay, this question was asked in SRF 2022 20, and it was given in a mm, matching. Okay, so you must remember where the headquarter was given of International Society of Soil Science. Okay, so the next one is the surface area of sand. What is the surface area of sand? 0.1 meter square per gram. So if you take 1 gram of soil, and if you measure the surface area of sand, how much surface it covers, 0.1 meter square per gram. Similarly for silt and clay, it is very important. So for similarly for silt and clay it is 1 and 10 to 1000 meter square per gram. Okay. Okay, the next thing is, if it is soil is called sand, so there should be more than 85% of sand should be there, and the clay content should be below 15%, then it will be called as sand. Okay, similarly for silt it is more than 80% and the clay content is less than 12%. But in clay soil, if you are saying a clay soil, then the clay content should be more than 35 percentage. Okay. Okay, the next thing is how to measure this soil texture. There are two methods: international pipette method, which is more accurate but time consuming. You must remember, more accurate but time consuming. Generally we use Boyko's hydrometer method. It is based on the density difference or dispersion and sedimentation, which follows Stokes law. Stokes law. Okay. What do you mean by Stokes law? The density of in the soil is the soil particle which are falling under the force of gravity. Okay, so the rate of fall is directly proportional to the square of the radius of the particle. Okay, this is given by Stokes law. So if you are using a Boyko's hydrometer, then it follows Stokes law, which is based on dispersion and sedimentation. Okay, so the observation should be taken at 5 minute and 5 hour. Okay, we are using sodium hexametaphosphate for deflocculation of soil aggregates. Okay, after that, in in a cylindrical jar, we are agitating the soil solution. Okay, then there will be, then after transferring into a cylindrical measuring cylinder, uh, the particle starts to this sediment. Okay, it will start to settle down. So the first particle which will settle down is sand, followed by clay and silt. Okay, so based on that we have to take observation. From that observation with some calculation we can know the textural class of that particular soil. Okay, the textural class was given from USDA by Whitney, and it was modified by Davis and Bennett. Okay, you remember this thing. Okay, here is a point we should remember: the silt particles are more prone to water and wind erosion. Okay, more prone to water and wind erosion. Okay, then comes to the soil structure. There are different types of soil structure. Okay, when it is natural, then it is called as peds. Okay, when it is artificial through different cultural practices, say suppose tillage operation, it is called as clod formation. You might have heard it, clod formation. Then the then the classification of soil structure goes like, there are four classes: spheroidal, platy, prismatic, and blocky. Okay, among those things, spheroidal is seen in grassland and it is best for agricultural purposes. Similarly, platy structure is formed due to compaction. Okay, due to heavy machinery, there will be compaction in the soil. So, due to that, platy structures are formed, which are seen in forest soils. Similarly, the prismatic can be of two types. It is columnar, okay, or angular. Okay, columnar or prismatic. This columnar structure is seen in subsurface horizon of salt affected areas of arid and semi arid regions. Similarly, the blocky, it can be blocky and subangular. Okay, based on the angle of that, it is seen in humid region. Okay, next comes the bulk density of soil. Okay, this is the soil bulk density, which is the ratio of mass of dry soil to the volume of soil sample. Okay, mass of dry soil to the volume of soil sample. Okay, it is called as apparent density. Okay, you must remember, question will be asked like, which is called as apparent density. Bulk density is the apparent density. Okay, similarly, the particle density is also called as true density. Why it is called a true density? Because it takes in account the solid portion. Okay, the solid portion, here you can see the solid portion of soil. Okay, it is not including the other air or soil water. Okay, but here it accounts the total volume of soil expressed in centimeter cube. Okay, this is called as true density. Truly we are giving us solids. Okay. Okay, so for bulk density, what we are using for uh, measurement, how we are doing for bulk density, we are using core sampler. core sampler. Similarly, for measuring the particle density, we are using picnometer. Okay, picnometer. Okay, okay. The thing is, the typical value of soil bulk density ranges from 1.1 to 1.6 gram per centimeter cube. Similarly, for particle density, it is double of bulk density. Okay, 2.6 to 2.7. Next one comes your void ratio, which is the index of fractional volume of soil pores. Okay, which value generally ranges from 0.3 to 0.3 to 2.0. Okay, then the followed by we'll start by with the mass wetness or gravimetric observation you have to take. For mass wetness is the water content. Okay, then the volume wetness is nothing but the volumetric water content. Okay. Okay, the next one is the pore space. Pore space. This is the formula given by pore space. This is bulk density. Bulk density by particle density. 100 minus, this is the formula. Okay, so using this formula, if you know the values of bulk density and particle density, you can analyze or you can know what is the pore space. Okay, in general, sandy soils have pore space ranging from 30 to 50. Okay, medium and fine texture soils 40 to 60%, and compact soils have 25 to 30%. Okay, this is important, guys. Total pore space is plus or minus 50% of water in the topsoil, which is ideal for any kind of crop production. Okay, so based on the pore size, we can have micropores and macropores. If the pore size is below 0.6 millimeter dia, then it is called as micropores. Similarly, if it is more than 0.6 mm, then it is macropores. Okay, guys. Okay, the next one is water retention. What do you call by water retention, and what are the factors that affect water retention? There are several factors. Okay, among those, cohesion, adhesion, and surface tension are most important. Okay, cohesion is the attraction between same molecules. Okay, same or similar, but adhesion is the attraction of water molecules with solid surface, because solid surface and water both are different, so dissimilar molecules are attracted, then it is called as adhesion. Okay, surface tension is the result of a greater attraction of water molecules and with each other and then the above air. Okay, surface tension. Soil moisture tension. What is soil moisture tension? Soil moisture tension is the nut is the tenacity with which means the tenacity with which water is retained in the soil. Okay, in the soil pore, it's called as soil moisture tension. Soil water potential is expressed in various forms. It can be expressed as 1 kg of centimeter square, or 760 of mercury column, or 1023 centimeter of water column. Okay, this is called soil water potential. You might be knowing 1 bar is equal to 0.986 atmosphere. 1 bar is equal to 0.1 0.9 atm. Okay, 10 bars is equal to SI unit. In SI unit is 10 bar. Okay, or megapascal also we can say. The viscosity of water is 0.0089 poise at 25 degrees Celsius. At 20 degrees Celsius, what is the viscosity of water? 0.01 poise. Okay, viscosity. Okay, the next one is the kinds of soil water. Okay, there are different kinds of soil water: gravitational water, capillary water, and hygroscopic water. Gravitational water is nothing but after irrigation or after rainfall, the water which is drained out with the force of gravity, with the help of gravity, is called as gravitational water. Okay. Uh, After 2 to 3 days of irrigation, the gravitational water stops, ceases. At the time, it is called as field capacity. Okay. Hmm. The second one is the capillary water. The capillary water is nothing but the water held by micropores. Micropores, not macropores. Micropores. Okay. The third one is the hygroscopic water. Okay, it is the water which is absorbed by the particles of dry soil. Okay, dry soil from the atmosphere, and it is held as a very thin, very thin layer, and due to adhesion or attraction between surface of particle and water molecules, this water is very hard to derive from by the plant roots. Okay. Okay, so therefore capillary water is the water which is available to plant, only water that is available to plant. Okay, for its utilization. Now comes the classification of soil water. There are two classification. One is physical classification, another is biological classification, right? So in physical classification there are three kinds of water, as I told before. Okay, hygroscopic water, hygroscopic water, capillary water, and gravitational water. Okay, water held tightly to the surface of soil particles by absorption is called capillary hygroscopic water. Okay, hygroscopic water, what is the potential? 31 atm or 31 atmosphere to 10,000 atmosphere. It is called hygroscopic water. Similarly, for uh, capillary water, what is the potential? It is from 31 to 0.3 atm. Okay, for gravitational water there is no such potential. Okay, the water which moves freely in response of gravity, as I told before, is called as gravitational water. Okay, gravitational water. Okay, and the next one is the biological classification, which is also three. Okay, available water, unavailable water, and superfluous water. Available water which is available to plant, and unavailable water which the plant can't extract water or utilize water for its daily purpose or metabolic purpose. Okay, or for photosynthesis, I suppose. Okay, then superfluous water also, it is not available to plant. Okay, now comes the soil moisture constants. Okay, soil moisture constants. What are soil moisture constants? There are different soil moisture constants. Mean at a particular uh, tension, or at a particular uh, potential, the water content will be same. So it is called soil moisture constants. Okay. So as we say, the maximum water holding capacity of soil or saturation capacity, it never changes for a particular soil. It may change from soils to soil or texture to texture. Okay, but it won't change for a single or a particular texture of soil. Okay, that's why it is called as soil moisture constant. The value will be constant forever. Okay, the first one is saturation capacity. What is saturation capacity? Saturation capacity is the soil water content when all the macropores and micropores are filled with water. Okay, so then the soil is said to be at maximum water holding capacity. Okay, the tension of water at soil saturation is almost zero. Okay, you must remember this. At saturation capacity, what is the water tension? Okay, because there is no tension in this system. Okay, so there is plenty of water, so there is no tension. Okay, so the tension is zero. Okay, equal to free water surface. You remember this thing, this is a very important. When saturation capacity is the 4 times of wilting point and 2 times of the field capacity, 2 times of field capacity and four times of wilting point. Okay, the next one is field capacity. You know, field capacity is the water content of a soil at the upper limit of available water range. It is the amount of water after it has been saturated and allowed to drain for 24 hours. Okay, the soil moisture tension at field capacity is 1/10 to 1/3 atmosphere. Okay, this is important, guys. After a day or so, once the micropores have been emptied in the under the action of drainage due to gravity, okay, then the micropores hold the water more tightly. This is called as field capacity. This is the upper limit of available water. Okay, upper limit of available water. Okay, the next thing is moisture equivalent. Moisture equivalent. What is moisture equivalent? The amount of moisture retained by initially saturated soil after being subjected to centrifugal force, which is 1000 time of that of gravity. Okay, for 30 minutes. For 30 minutes is called moisture equivalent. For sandy soil, uh, the field capacity is more than moisture equivalent. Okay, because when you are giving a force of 1000 times of gravity, the soil particles in a sandy soil can't withhold more water. Okay, so only the moisture content at field capacity is more, okay, in sandy soil than moisture equivalent. Okay, similarly for clay soil, the field capacity is less than moisture equivalent, because it has the power to absorb water, to retain water. Okay, as the clay content of soil increases, go on increasing, the retaining power of the soil, the retaining power of water of the soil, goes on increasing, is right. Okay, the next one is the permanent wilting point. Okay, this is the lower limit of available water range. Okay, upper limit is the field capacity, lower limit is the permanent wilting point. Okay, it is also known as wilting coefficient. Hmm. You see here, the what is the main thing is the potential. What is the potential? It is minus 15 bars, or it can be said as minus 1.5 megapascal. Okay, 1.5 megapascal or minus 15 bars or 15 atm. Generally it ranges from 7 to 32. For an average we have taken as 15 bars. Okay, okay, moisture content at which wilting is completed and the plants automatically die is called as ultimate wilting. Okay, ultimate wilting point. Ultimate wilting point, where the plant dies. Hmm. As we discussed, hygroscopic coefficient, what is the value? Minus 30 bar to minus 3 megapascal. Okay, at ultimate wilting point, minus 60 bars. Okay, okay, now comes the potentiality concepts. Okay, in soil there are different kind of forces acting on the soil, which causes the movement of soil particle, which movements of the water molecules in the soil system. Okay, which is in a total it is called as water potential or soil water potential. Okay, there are different aspects of soil water potential or different components of soil water potential. One is gravitational potential, then the second one is the pressure potential, and the third one is the osmotic potential. Okay, what is soil water potential? We came to know here. Okay, so then here, as I told, gravitational, metric, and osmotic potential. Okay, okay, what is osmotic potential? It is only due to solute, present of solute. Okay, so if there is presence of solute in the soil, then it will lead to osmotic phenomena. Okay, so mainly when the water is transporting the root. Okay, root water, it is a root, say suppose it is a root, and the water is moving through the system, through the root. When the root absorption occurs, it moves the osmotic potential. Okay, here exists the osmotic potential. Okay, or any salt is there in the soil, which leads to osmotic potential. Okay, similarly, the gravitational potential, Okay, the gravitation potential is nothing but due to the action of gravitational action, gravitational energy. Then it is called as gravitational potential. Okay. Okay. Now comes the pressure potential. Okay, pressure potential may be defined as the work that a unit quantity of water in an equilibrium soil water system is capable of doing when it moves to another equilibrium system identical in all respect except that there is a reference pressure. Okay, say suppose is a waterlogged soil, this is soil system. Okay, this is soil, and there is a standing water of 1 centimeter. Okay, 1 centimeter for suppose. So this creates the pressure potential. Okay, pressure potential. When the soil water is below the water table, it is a hydrostatic pressure greater than that of atmosphere pressure. Okay, and the pressure potential is positive. Okay, which is occurred in submerged potential. Okay, submerged, as I said here it is positive, also called as submerged potential. When it is above the depth of water table, it is at a pressure less than the atmospheric pressure. Okay, pressure less than the atmospheric pressure, so only the potential is negative. So negative potential is referred as to suction or tension. Okay, in saturated soil or submerged soils, rice soils where rice what standing water is there is the pressure potential is positive. Okay, the next one is when the water is at a free water surface, the pressure potential is G. Okay, you must remember this one. Okay, here comes the metric potential. What is metric potential? Metric potential is due to nothing but due to it is created due to the soil matrix. Okay, soil matrix, soil micropore, macropore. Okay, due to matrix, the metric potential is created. The soil water in unsaturated soil has no pressure potential but has only metric potential. Unsaturated soil, unsaturated soil, there is only metric potential. Okay, metric potential, only metric potential. You must remember. Okay, okay. So you must remember in unsaturated soil, the pressure potential is zero. Okay, pressure potential is zero. Okay, but in saturated soil the pressure potential is positive. Okay, positive. This is the thing you must remember. Okay, then but when it comes to metric potential, okay, when it comes to metric potential it is negative for unsaturated soil. Okay, unsaturated soil it is negative, but pressure potential for unsaturated soil, pressure potential for unsaturated soil is zero. Okay, because there is no water movement. Okay, there is no standing water in unsaturated soil as it indicates, right? Okay, now comes the soil water release curve or soil moisture characteristics curve. Okay, soil moisture characteristics curve, SMCC. The curve of metric potential versus water content is called as SMCC. If the water less water, then more tension. Okay, the water is lesser, then there is more tension. Means the plant has to uh, spend more energy for deriving water, so there is more tension. Okay, in the soil. At a given tension, finer textured soils retain more water. Okay, as I told, clay particle retains more water. Okay, okay. So this is the curve. You can see here the clay curve, the sand curve. Okay, the clay curve forms I pattern, but the sand, as you can see here, okay, L shape, sand, clay. Okay, sand. This you must remember. So this happens. Okay. Uh, Why it happens? The soil moisture characteristics curve. There is one thing is called ink bottle effect. Okay, ink bottle effect, due to drying and wetting curves. Okay, due to drying and wetting curves, there is formation of hysteresis. Hysteresis. Hysteresis is nothing but, you see here. Okay, for everything there is a curve. Okay, and here, okay, as we draw another drying and wetting curves. Okay, drying and wetting curves, you can know it will come a I shape. Okay, I shape. This is drying curve, this is wetting curve. Okay, okay, so at a particular tension, the moisture content in the drying curve is more. Okay, at a particular tension, the moisture content in a drying curve is higher than wetting curve. Okay, this happens, why this happens? Okay, this happens due to geometrical non-uniformity, shape shape and interconnected pores, entrapped area. Okay, then swelling and sinkage property of the soil. The next one is the available water. What is available water? As I told you, if you field capacity and permanent wilting point, this range is called available water. Okay, available water. Available water capacity. What is available water capacity? As I told you, wilting point and field capacity. The units, it is unitless, or it can be written in mm. Okay, it is measured using field and laboratory methods, and there are different methods. Okay, of available water will be studying how to measure. Measurement of soil moisture. There are two ways. Okay, there are two ways. One is direct and another is indirect method. Okay, indirect method. For direct method, there is gravimetric. Okay, by drying the soil at 100 0 and 105 degrees Celsius. Okay, by drying the soil, it is called gravimetric method. Or for alcohol burning. For field capacity, the alcohol required is 1 ml. Okay, for permanent wilting point, 0.5 ml. 0.5 ml. Okay, alcohol is required. Similarly, there are other direct methods, which are gypsum suction plug. Okay, gypsum suction plug. Okay, not gypsum blocks. Okay, it is a indirect method. Okay, it is indirect method. Gypsum blocks. Okay, but gypsum suction plug is direct method. And then another direct method is infrared balance. Infrared balance. Now comes the indirect methods. What are the indirect methods? Indirect methods are tensiometer, with the use of tensiometer. Okay, then gypsum block, as I told. Okay, then there are neutron scattering. Okay, gamma ray attenuation. Gamma ray attenuation. Then there are thermal and remote sensing methods are there. But here is the neutron scattering method. This is important, and tensiometer. This is also important, as well as the gypsum block. Okay, you all know tensiometer is a tube. Okay, where the pressure gauge will be attached, where the pressure, the tension can be measured. Okay, this is a porous plate. Okay, tension below 0.85, below 0.85 bars in sandy soil, it is suitable. Okay, it is also called as aerometer. Okay, aerometer. It is developed by Richards and Gardner. Okay, Gardner. This is all about tensiometer. The second thing is gypsum block. Gypsum block, it is not suitable, not suitable for sandy soils. Okay, the measured pressure, how much we can measure, 0 minus 1 to minus 15 bars. Okay, within this range we can measure. Okay, but in sandy soil, the potential remains below 1, is not it? That's why for the tensiometer we are using for sandy soils. Okay, tensiometer. If you're not understanding, and again I can repeat this. Okay, neutron moisture probe is also called as neutron gauge. Okay, moisture depth, moisture gauge, depth moisture gauge. Okay, there are there is a probe from which radium is there. Okay, and there is a attachment of barium and americium. Okay, barium and americium. When the neutron from the probe is released and when it hits the soil, and if the soil having higher water content, then the rate of movement of this neutron, okay, it becomes slower. So in this way the moisture content is higher. Okay, moisture content is higher. This way you have to interpret. And it is not suitable for organic soils, because carbon and hydrogen, oxygen is as the constituent. Okay, it may affect or interfere with the neutron flow. Okay, and for upper 15 centimeter soil it is not suitable. Okay, this is all about neutron probe or neutron moisture. There is another apparatus called pressure plate. Okay, pressure plate, where a required pressure is created, say suppose for field capacity. Wait. Okay, pressure gauge, pressure plate apparatus. Okay, where a required pressure is created using the uh, electrical. Okay, using the required pressure is created for field capacity 0.3 atm, for permanent wilting point. Permanent wilting point, 15 bar. Okay, so there will be a porous plate inside. Okay, porous plate inside, where the soil has to be kept. After saturation, the porous plate has to be kept inside a pressure chamber. Okay, inside the pressure chamber it has to kept. Then we'll create a required pressure of 0.3 atm, say suppose for field capacity, or it may be in 15 bar for measuring the permanent wilting point. Okay, so after putting this saturated soil up and providing the required pressure, then at that pressure what is the moisture content, at that pressure what is the moisture content. Okay, in this way we'll get a graph. Okay, so this is also can be done using pressure plate apparatus. Okay, so who gave the pressure plate apparatus? Okay, in the last lecture we have discussed. Okay, kindly go. The next one is the infiltration. Infiltration is nothing but movement of soil into the soil. Okay, through the when there is two system. Okay, two system, two system. This is soil system. This is atmosphere. When water moves from one system to another system, okay, then it is called as infiltration. Is not it? But what percolation is nothing but percolation is the movement of water inside the soil system, but beyond the root zone. Okay, beyond the root zone, if it is going, it is percolation. In the previous terminology class, I have discussed clearly about these two terminologies. Okay, please go through it. The next one is the classification. Okay, when 0 less than 0.25 centimeter per hour, it is called very slow infiltration. Similarly, for slow 0.25 to 1.25, moderate 1.25 to 2.5, for rapid more than 2.5 centimeter per hour. Okay, so very slow infiltration where it will occur, very clay soil. Similarly, for clay soil, slow For sandy loam, moderate, and rapid in case of deep sandy or silt loam. If there is more rainfall intensity, it reduces the infiltration rate. How? If more intensity, then it will clog the pores, is not it? It will displace the soil from one place to another. Okay, then the soil pores will get clogged, is not it? Then how the water will move? How the water will move? Infiltrate. Okay, so when there is more rainfall intensity, okay, so it will reduce the infiltration rate. Okay, similarly, if there is vegetative cover is more, the infiltration rate is more. Okay, compared to bare soil. And warmer soil, the soil having somewhat more temperature, soil temperature is more, then infiltration also it is more. Similarly, double ring infiltrometer. Using this double ring infiltrometer or ponding method, we measure the infiltration rate for different soil types. There are different infiltration rate. For sandy soil it is more than 20 millimeter per hectare. Okay, for sandy and silty 10 to 20. Okay, for loamy soil it is 5 to 10. For clay soil it is 5 to 1 to 5, and below 1 millimeter per hectare is sodic clay soils. Okay, sodic clay soil, because sodium is present. Sodium is a dispersing agent. Hmm. Deflocculating agent. Deflocculate, it will deflocculate the soil particle, and clogging will be there. So the movement of water also will get slower. So only sodic clay soils having less than 1 millimeter hectare of infiltration rate. Okay, clear. Okay, the next thing is the permeability. The readiness with which a porous medium transmits fluid is called permeability. Okay, it decreases with increase in fine texture. As the fine texture increases, the readiness of flow or transmission of fluids inside the soil reduces. Okay, right. This is the graph you can see here. Okay, how the sandy soil behaves, how the clay soil behaves, and this is the accumulated infiltration versus time graph. Okay, nothing else is here there. Okay, this is the same thing. Fine sand, fine sandy loam and silty loam, how the graph. Okay, huh, right. Percolation I have discussed in the terminology classes. Okay, and this class also I told what is percolation, what is seepage. Seepage is the downward and lateral movement. Hmm. When seepage occurs and lateral movements occurs, it comes through a valley. Okay, this is soil, and after irrigation it is valley, suppose. Okay, this is also soil, and the water moves laterally and comes up with a opening. Okay, here, then it is called wet spots. Okay, interflow is the lateral seepage of water in relatively pervious soil above a lesser pervious soil. This is interflow. Then comes your water movement in the saturated and unsaturated soil. Okay, saturated and unsaturated soil. Okay, let's go through it. What is water movement in the saturated soil? Okay, saturated, under saturated soil, when all soil pores are completely filled with the water, the movement is referred as saturated flow. In saturated soils, water movement occurs through macropores only. The relative number and continuity of these pores greatly influence the movement. Okay, it depends on the continuity and the number of macropores. Okay, the flow, the saturated flow in the soil depends on the number of and continuity of this flow. If continuity is broken, then movement is reduced. Okay, in sandy soil the movement of water is therefore faster, it is faster than clay soil. Okay, as in sandy soil, there are more larger macropores and the water movement is easier, is not it? Water in the saturated soil is not under any tension, and the flow follows either Poiseuille's law or Darcy's law. You must remember. Okay, saturated soil flow, saturated soil, water movement in a saturated soil follows either Poiseuille's law or Darcy's law. Okay. So how to measure this one movement? We can use permeameter or consolidometer. Okay. There are different types of, okay, permeameter, constant head method and falling head method for different soil different. Okay. Anyway, this is the Poiseuille's equation. This is the Poiseuille's equation, must know. Okay, the equation says that the flow is directly proportional. Okay, directly proportional to the fourth power of the radius of pore. Radius of pore. In Stokes law, what you studied? Radius of soil particle. Soil particle. Here, soil pore. Understood? This is the law. Okay, which indicates larger size pores for sandy soil permits faster movement of water in the soil with small size pore, more than the small sized pores or clay soils. Soils have small pores and the pores from narrow tubes. Okay, in narrow tubes the movement is slower. Okay, anyway. Okay, here's Darcy law. Darcy law in 1956. Darcy gave the Darcy law, which is the relationship between water flux and energy gradient. Darcy law states that velocity of water flow is directly proportional to the difference of hydraulic heads and inversely proportional to the flow length. Okay, difference of hydraulic heads and inversely proportional to the flow length. Is not it? Here's the Darcy law. Okay, K is the hydraulic conductivity. Hydraulic conductivity. Hydraulic conductivity is the nothing but the ease at which water is conducted in the soil. How much easily the water is conducted in the soil system is called hydraulic conductivity. Now comes the water movement in the unsaturated soil. Okay, as the water content decreases from the point of saturation with progress of drainage, air slowly gets into the pore system. Okay, larger pores are emptied, and which is first occurrence, larger pores get emptied. Okay, then this results in the marked decrease in the rate of water movement in the soil. The flow becomes a function of the water content. The flow becomes the function of water content at, okay, of the soil, and is referred as the unsaturated soil. Okay, as per the Darcy law, what it says, cross sectional area directly proportional to the cross sectional flow is directly proportional to the cross sectional area. As unsaturated soil, the flow water, the cross sectional area become reduces. Is not it? In unsaturated soil, so the flow becomes the function of water content. The more water content, more area of contact, more area of contact, or more uh, cross sectional area it can cover, so more flow. If less water, the opposite thing will happen. Is not it? In unsaturated soil, the hydraulic head becomes non-existent and gravitational potential is less important, whereas the metric potential comes into full play. Okay, as I told before also, in the metric potential, in unsaturated soil only the metric potential plays a major role. Is not it? Right. So there is a vapor movement also, besides this unsaturated and saturated movement, there is water vapor movement also. Okay, at a soil moisture potential of minus 15 bar, the continuity of liquid film is broken. Is not it? Below permanent wilting point, the continuity is broken, so water forms a vapor. Okay, in the vapor form it moves by the vapor pressure gradient is the driving force, main driving force of water vapor movement in the soil. The vapor pressure of soil moisture increases with increasing soil moisture content. Vapor pressure decreases with the increasing soluble soil content. Is not it? The water vapor movement is significant in moist range. Okay, only in moist range, not in wet range. as it is negligible. There is no vapor. Okay, wet range is, there is plenty of water present, so there is no chance of or no need of any vapor movement. Okay, so in moist rain the vapor movements occurs. Okay, it is very interesting to note that maximum water vapor movement occurs in soil just before the permanent wilting point reached. Okay, before permanent just before a permanent wilting point, the maximum water vapor movement occurs. Okay, which is moist range, is not it? At this stage, water movement is a greater importance for growth and survival of the plant. So at ultimate wilting point, only plant get die, is not it? So so this completes your today's lecture. I hope you guys are clear. Okay, if you have any day any if you have any doubt, you can contact. So this is Grija signing off for today's. So we'll meet in the next class. Take care and prepare well, students. Thank you.